A rover snapped a routine sky check on Mars. Hours later, the internet was on fire. A streak that should have been a boring blur looked way too clean. Agencies stayed quiet. Two expert camps formed fast. Camera trick, or something real. Settle in. We are going to test this together. Picture the scene. October 4th, 2025. Perseverance is parked in Jezero crater, running a scheduled navcam sequence. These are utility cameras, black and white, built to steer around rocks, not to make headlines. At 33 milliradians per pixel, they are not meant to resolve crisp objects millions of kilometers away. Yet one sequence of rapid frames gets stacked by people watching the raw feed. Suddenly, an elongated glow pops out, about 4 times longer than it is wide. Not a dot, not a smudge, a bar of light in the Martian sky. So what are we actually looking at? Option 1. A camera artifact created by motion during stacking. Imagine a car at night, long exposure, headlights turn into lines. The car did not stretch. Your sensor integrated time into space. Now put that idea above Mars. The interstellar visitor known as 3I Atlas is racing across the background. Over roughly 10 minutes, it travels tens of thousands of kilometers relative to the rover. If you stack hundreds of frames to beat down noise, you also smear the signal. A tidy streak appears. Case closed. Right. Option 2 refuses to die. People notice the center looks white while the outskirts hint green. If a big green coma surrounds a small nucleus and you smear sideways across many frames, you should flood the stack with green. Yet the middle stays stubbornly white. That is strange. Not decisive, but strange enough to keep the debate alive. Here is where you and I come in. Viral stories collapse unless we rebuild them with first principles. We will translate the angular resolution of the camera into kilometers at the target distance. At about 38 million kilometers, each pixel spans roughly 12,500 kilometers. If the streak measures near 50,000 kilometers long, that maps to about 9 or 10 minutes of integrated motion at around 90 kilometers per second relative to Mars. That is exactly the time window the stackers used. The math likes the artifact story, but images are not only geometry, they are also chemistry. Green usually means gas, often diatomic carbon fluorescing under ultraviolet sunlight. Early in September, ground observers reported the object shifting from reddish dust dominant to green gas dominant. Later, spectra complicated that picture by suggesting the usual green maker was depleted. That tension matters because color encodes composition. Composition shapes brightness. Brightness shapes what a stack will emphasize, which loops us back to why that white core refuses to go away in the processed frames. Meanwhile, institutions that could referee seemed to step off the field. NASA entered a government shutdown on October 1st. Websites stalled, public affairs paused. That explains some silence. Yet the European Space Agency had announced observations. China and the United Arab Emirates had orbiters in position and strong incentives to showcase results. For a few crucial days, nothing official appeared. Silence is not proof of anything. It is still a data point. And it raises the stakes on independent analysis. Here is our plan for the next 2.5 hours. Keep the tone energetic. Keep the standards high. We will test the camera math. We will test the color story. We will test the chemistry from space-based spectra. We will test the orbit with post-perihelion fits when the sky geometry gives Earth a look again. Every time we pose a question, we will pin it to a fact you can check. Every time we speculate, we will frame it as a question you can argue with. Could this all be a perfect storm of motion blur and wishful processing? Could it be the first time a rover on another world accidentally photographed an interstellar object with a shape that is not easily explained? Here is where the story gets really strange. Both possibilities remain open because the first image is just ambiguous enough to support two narratives. The only way forward is to widen the evidence base and force these explanations to compete. Quick favor while we set up that duel. If you love this kind of shared investigation, tap subscribe so you do not miss the next dataset when it drops. And tell me your first instinct in the comments. Artifact or elongated object? Say why. Then watch how your view evolves as the evidence changes. That evolution is the whole point of science, and it is about to be fun. Two camps formed within hours, and they still look at the same pixels and see two different skies. That is the heart of this story. On one side are the imaging specialists who say the streak is exactly what you get when you stack lots of noisy frames while the target is moving fast. On the other side are observers who cannot get past the color structure. They point to a bright white center with green around the edges and ask how a pure smear would keep that white core intact. Today, we slow down and let both cases make their best arguments. Start with the smear team. The navcam is not a telescope that tracks on the object. It stares in a fixed direction while the interstellar visitor slides across the field. Each raw frame catches a slightly different location of the same faint source. When you stack frames, random noise averages down, but any real source gets added together along its path. The result can look like a clean bar of light, even if the thing itself is compact. At the Mars distance involved, the angular scale of the navcam works out to about 12,500 kilometers per pixel. Over roughly 10 minutes, the object can travel on the order of 50,000 kilometers relative to the rover line of sight. Now, imagine that distance as a brushstroke painted a few hundred times. The stroke sums into a neat, elongated feature. If you have ever photographed a car at night with a long exposure, you already know this effect in your bones. Headlights turn into lines. The car does not stretch. Time writes a shape on the sensor. The smear team adds another practical point. The stackers were likely aligning on the stars or on the rover frame, not on the moving target. That choice matters. If you do not register on the object, you guarantee that it will smear. Stack enough frames, and at some integration time, the streak length naturally matches the distance traveled. The numbers from the scene line up well with the observed length. From that perspective, the clean bar is not a mystery. It is a predictable signature of how the data were processed. Now hear the color camp. They accept the smear math but push on what the smear should look like if a large green coma surrounds a small nucleus. In that scenario, every frame contains a lot of green light from gas around the core. Stack sideways through the coma, and you bring a river of green into the center of the composite. So why is the midline so white? Why do hints of green hug the flanks instead? Their argument is geometric and photometric. If the coma dominates, the integrated color bias should skew green where the streak is brightest. If the white remains dominant in the core, then either the nucleus or some inner region is contributing a brighter or different spectrum that resists being washed out by the coma. That could mean a physically extended bright source, or it could mean the colorized versions overweighted certain channels. The data are persuasive either way until you inspect the processing details, which are rarely standardized in viral posts. Both sides then point to the same follow-up need: calibrated data from instruments that can resolve more than a few dozen kilometers across at the flyby distance, and that can separate flux by wavelength in a controlled way. In other words, professional Mars orbiters and space-based spectrometers. If the streak is pure motion, high-resolution imaging should show a compact central source convolved with a modest coma. If any extended white structure exists, better cameras should reveal that geometry directly or in light curves that carry the fingerprint of a long body. So, which camp should you trust right now? The honest answer is that both arguments hold water in different bins. The motion math is clean and recreatable. The color tension is real enough to deserve an explicit model rather than a hand wave. Our job in the next parts is to treat each claim like a hypothesis and hit it with independent tests. We will follow the photons into chemistry. We will bring in spectra that reported an unusual mix of carbon dioxide, carbon monoxide, and very little water. We will examine why nickel showed up early and iron did not. Each of those facts pushes the color debate, because composition drives color and brightness from the inside out. Before we leave the two camps, do something useful in the comments. Pick one prediction from each side that would change your mind and write it down. For the smear case, maybe you want a professional image that reproduces the streak length from the measured motion within 10%. For the color case, maybe you want a calibrated stacked image where the central color stays white even when green emission lines are isolated. The best science questions are the ones that suggest clean tests. We have them, now we run them. Silence is usually boring. Here it was, deafening. The question on everyone's mind was simple. Why did so many space agencies go quiet at the very moment when their images could have settled the argument? NASA entered a government shutdown on October 1st. That part is routine politics. Non-essential staff are furloughed. Press offices slow to a crawl. Many websites freeze. Raw rover images can still appear because those pipelines are automated. Processed data that requires humans often stalls. That explains part of the gap. But the quiet did not stop at the American border. The European Space Agency had announced that its Mars missions would observe the interstellar visitor during the first week of October. China has a track record of rapidly publishing Mars images for national pride. The United Arab Emirates built a mission that exists in part to share atmospheric science with the world. All three were positioned to capture something during the closest approach. Yet, for several days, nothing. No calibrated images, no teaser thumbnails, not even a short note that processing would take time. So what is the most charitable read? Scientists are careful. Teams pre-plan observations for months. They calibrate detectors. They document everything. If you rush a release and make a mistake, you pollute the record. You also risk being scooped in journals if you tip your hand too early. Review processes take time. Multiple teams need to cross-check each pipeline. Silence in that context can be professionalism rather than secrecy. Now the harder read, silence can also be a choice. Rival institutions sometimes coordinate when a result is ambiguous in a way that could trigger confusion or media panic. We have protocols in astronomy that encourage verification before dramatic claims. Even without anything dramatic, agencies may decide to hold until they can present a clean package of images, spectra, and plain language context. That is not proof of a cover-up. It is evidence of risk management. Here is why the quiet still matters as data. Public missions usually share at least a minimal success confirmation after high-interest observations. A sentence like "acquisition successful" can cool wild speculation. The absence of even a simple status line is unusual enough to log in our notebook. It does not tell us what is true. It does tell us that communication strategy became a variable during a critical window. Meanwhile, the internet filled the vacuum. Forums and feeds did what they always do. They rewarded confidence more than accuracy. Theories multiplied. Some were thoughtful. Many were not. This is where we tighten our own rules of engagement. We will not assume motive from silence. We will not read intent into timing coincidences. We will write down what silence can and cannot mean, then move back to tests that do not depend on statements. There is a practical reason to care about the institutional timeline. The best cameras during the Mars flyby were not on the ground. They were in orbit around Mars. High-resolution images could, in principle, turn a smear back into a shape by measuring how brightness falls from center to edge across multiple wavelengths. Spectrometers could check the nickel and iron puzzle with higher signal-to-noise. If these datasets exist and are clean, they will weigh more than any argument built from stacked navcam frames. The longer they take to appear, the more the public conversation will drift toward absolutes that the data might not support. So, how do we hold curiosity without sliding into cynicism? We set expectations. It is normal for processed releases to lag raw feeds by days or weeks. It is normal for non-American missions to follow their own schedules. It is also normal for scientists to prioritize journals over social video timelines. Normal does not mean satisfying. That is why our plan does not wait on any single press release. We can push the story forward with physics. In the next part, we will do exactly that. We will build the smear from first principles and show you how cameras turn motion into shape. Then we will stress test the limits of that explanation against the white core and green edges that bothered so many observers. By the time we are done, you will be able to look at a stacked image and say whether the length and brightness profile makes sense for the exposure time and the relative speed. If agencies release the high-resolution frames tomorrow, great. If they do not, we will still be ready to evaluate them when they do. Curiosity does not need permission, it only needs method. Cameras are honest in a mechanical way. They record exactly what light hits the sensor during the time the shutter is open. Cameras are also expert liars. They can turn time into shape. They can make a point look like a line. Understanding both facts is how we stop guessing and start testing. Begin with a simple experiment. You stand on a bridge at night. A car passes below. You open the shutter for a few seconds. On the photo, the headlights smear into a brilliant stripe. The car did not become a ribbon. Your image is a sum over time. Each instant adds a little piece of light in a slightly different position. Add enough instants, and you have a line. That is stacking in spirit. Astrophotographers do it to beat noise. The sky is faint. Sensors are imperfect. Summing many short frames boosts real signal while random speckles cancel out. Now take that logic to Mars. The navcam takes a train of short exposures. The rover does not track the interstellar object. It holds still. Between frame 1 and frame 2, the target has moved slightly across the sky. Between frame 2 and frame 3, it has moved again. When you stack those frames in the rover reference frame, you are doing the bridge experiment with stars. The stars align nicely. The moving object lays down a breadcrumb path. Stack enough frames, and the breadcrumb path hardens into a white bar. The math is clean. Angular resolution is the link between pixels and distance. The navcam scale is about 33 milliradians per pixel. At roughly 38 million kilometers, that corresponds to around 12,500 kilometers per pixel. Relative speed matters next. The object is sprinting through the Martian sky at about 90 kilometers per second when you combine its retrograde path with Mars motion. Over 10 minutes, that is, roughly 50,000 kilometers. Divide by the pixel scale, and you get a streak several pixels long. That matches the elongated feature in the viral composite. The length is not magical. It is kinematics, written in grayscale. So why are people still uneasy? Because length is not the only clue. Brightness along the streak carries information too. If the object were a point source convolved with the camera blur, the intensity should fall off smoothly from a central maximum. If a large green coma surrounds the point, then stacking sideways through that coma should paint the streak with a green bias. Many processed versions keep a bright white center, with only hints of green toward the edges. That is the friction point. The smear is plausible. The brightness profile feels stubborn. Before we decide that brightness proves a shape, we need to audit the processing. Stacks are choices. What frames did you include? How did you register them? Did you equalize background levels before summing? Did you apply a high-pass filter that sharpens the midline? Did you map grayscale to color in a way that overweights the core? Viral images often skip these details. Two people can start with the same raws and produce very different looks, while both believe they preserved the truth. To break the tie, we need either controlled processing with shared parameters or independent tests that do not depend on cosmetics. There is a good independent test. Predict the brightness profile from first principles. Assume a compact core, plus a faint coma with some radius and a realistic falloff like 1 over r squared or steeper. Convolve with the navcam point spread function. March the source across the field in small steps that match the expected motion. Sum the frames, compare the result to the observed profile. If the simulated center stays white relative to the flanks without any physical elongation, then the color complaint softens. If you cannot match the white core without giving the core a real width, then the artifact explanation needs help. Another check uses the width of the streak perpendicular to motion. Pure smearing builds length. It barely widens the feature. If the observed width is larger than the point spread by a meaningful factor that suggests either heavy processing or an intrinsically extended source, measure the full width at half maximum across the bar. Compare to stars in the same stack. Numbers beat vibes. A third check uses time slicing. Instead of stacking the full 10 minutes, you stack consecutive short windows. If it is a smear, you should see a shorter streak that grows with the window length. If it is structure, you might see a similar width even in short stacks. Amateur communities can run this today using the public raw frames. The result will not end the debate, it will narrow it. So what if we do all of this and the verdict is still blurry? Then we pivot to instruments that sidestep the limitation. Mars orbiters with higher resolution can separate core from coma, even in short exposures. Spectrometers can tell us if the core and the shell have different colors that survive stacking quirks. Light curves can hint at shape if rotation modulates brightness in a steady rhythm. Here is the key mindset. Cameras lie when we let time and motion sneak into shape. Cameras tell the truth when we account for those factors ahead of time. In the next part, we will use color to challenge and support the smear at the same time. Green should mean certain molecules. Spectra say those molecules are scarce. That contradiction is not a problem. It is a gift. It gives us a hard question that only chemistry can answer. Bring your curiosity. We are going to open the spectrum and see what is really glowing. Green should be simple. In comet land, green usually means one molecule is partying under ultraviolet sunlight, diatomic carbon. Astronomers call it C2. Sunlight breaks larger carbon chains. C2 soaks up ultraviolet and re-emits in the green. Your eye sees a soft emerald fog around a tiny core. Case closed, except not here. Back up to early September. Telescopes on Earth catch the visitor during a total lunar eclipse. Perfect dark sky. The color flips. Earlier it looked reddish, which suggests dust reflecting sunlight. Then the coma turns green. That screams gas turning on. Naturally, you reach for the usual suspect. But when teams point spectrographs at the object, something odd happens. The C2 lines look weak. One paper even labeled the object severely depleted in carbon chains. So how do you get a green glow without much of the molecule that normally makes comets green? Two possibilities jump out. First, cyanogen. Astronomers shorten it to CN. It is a radical that also lights up under ultraviolet and can contribute in the blue to green neighborhood. If CN ramps up fast while C2 stays scarce, you can still end up with a perceived greenish halo depending on your filter choice and your eye response. Second, scattering. The coma contains dust grains of many sizes. Some sizes scatter sunlight in ways that bias color perception toward green when mixed with faint emission lines. Neither option is a cheat. Both are real physics. The trick is figuring out which combination actually dominated in September. Why does this matter for our smear debate? Because color is not decoration. Color is composition. If the coma is green because gas dominates, then stacking through a big gas halo should tint the streak. If the center remains mostly white in process stacks, that tells us the core or near-core region is either much brighter than the surrounding gas or emits a spectrum that resists being overwhelmed. That does not prove a long solid body. It does force us to quantify brightness ratios instead of eyeballing screenshots. Now widen the lens. Earlier space-based spectra reported a volatile mix very unlike many solar system comets. Carbon dioxide looked dominant. Carbon monoxide was present. Water was low by comparison. That recipe matters because it sets which molecules are available to glow and in what amounts. A carbon dioxide-rich coma makes strong sense for a green turn that does not feature much. C2, if other carbon-bearing fragments like CN are being generated efficiently, while carbon chains that feed C2 are relatively scarce. It also matters for temperature. Carbon dioxide starts puffing off at larger distances from the sun than water. That can make a coma look active earlier and change how the core versus coma brightness evolves as heat ramps up. There is another link. The same spectra that puzzled people about the green also reported metal lines later on. Nickel showed up early, iron lagged. We will dig into that in the next parts. For now, note the pattern. Multiple clues point to a chemistry set that is skewed compared to our local comets. Skewed chemistry can create skewed colors. Skewed colors can create misleading intuitions about shape if we do not model the light correctly before stacking. That is why we are being careful. So what test would unravel the green puzzle? A controlled imaging run with narrowband filters centered on the classic C2 bands, another on CN, and a continuum filter to catch dust scatter. Stack each set separately in short windows to minimize motion. If the green halo survives only in the CN band while the center stays white in the continuum, the color tension in the viral composite looks more like a processing and weighting effect than a structural revelation. If a bright elongated core remains dominant even in gas bands, then color stops rescuing the smear case and we have to consider geometry. Could this still be the usual story in disguise? Yes, comets are messy. Jets are patchy. Light bounces off grains that change size as they break apart. A small change in the spectrum can look like a big change in color when your eyes and cameras are not calibrated the same way. But that is exactly why the composition anchor is so useful. Spectra are less easy to fool than pixels colored after the fact. Here is the handoff. If color is composition and composition sets activity, then the next logical step is to ask what this object is actually made of in bulk. Space-based spectrometers have already sketched a surprising answer. A coma that seems to run on carbon dioxide and a metal story that refuses to behave. That chemical context will either rescue the simple smear or make it wobble. Either way, it is time to open the periodic table. If you want to understand why this object keeps defying our expectations, start with its breath. Most comets in our neighborhood wake up on water, warm them, and water ice turns into vapor that drags dust into space. Tails grow, colors shift. The playbook is familiar. This visitor brought a different script. Space-based spectra reported a coma dominated by carbon dioxide, with a meaningful slice of carbon monoxide and only a small fraction of water. That is a reversal of the usual pattern. It is like opening a soda and finding almost no water inside. The gas is driving the show. Why would a comet carry so much carbon dioxide and so little water? One idea is birthplace. If it formed much farther from its home star than our comets formed from our sun, then water ice could have been altered or depleted early, while carbon dioxide stayed locked in. Another idea is age. Interstellar travel is slow. Over immense time spans, cosmic rays can process the outer layers of objects, cracking molecules, changing what sits near the surface. You can end up with a skin that releases certain volatiles first and hides others until the heat rises. Both stories are plausible. Neither demands anything exotic. Composition matters because it sets the schedule. Carbon dioxide starts to sublimate at larger solar distances than water. That means this object can look active earlier than you expect. The coma can bloom well before a classic water comet would get going. That early activation changes the balance of brightness between core and shell. If the gas turns on while the nucleus is still relatively cold, the core might remain optically bright in reflected light while the surrounding gas dominates emission in narrow bands. Stack those scenes and you can get a stubbornly white midline, even while the outskirts look green in the right filters. Suddenly, the color tension we saw earlier feels more like a composition story than a shape story. There is also a thermal twist. Carbon dioxide sublimates vigorously as solar energy rises. Carbon monoxide does too once certain thresholds are crossed. Mix in a small but present amount of water, and you can build a layered activity curve that steepens rapidly with decreasing distance from the sunday. That is exactly what several production rates seem to do. Simple heating can make sharp bends when a molecular switch flips from off to on. You do not need intent for that. You need physics and the right inventory. Now bring in the metal teaser. While the gases were taking the stage, spectra began to show nickel lines earlier than many expected. Iron stayed shy until closer in. If your coma is rich in carbon monoxide, you have one of the precursors needed for a well-known industrial pathway on Earth that can move nickel into the gas phase at relatively low temperatures. That is not a claim that the same process runs in space the way it runs in a refinery. It is a reminder that chemistry is opportunistic. Give it the right partners and it finds a path. A carbon dioxide heavy and carbon monoxide friendly environment could create the conditions for nickel to appear before iron. That does not settle the argument. It does place the metal oddity inside a composition that could support it without magic. So what would we expect to see as the object moved toward perihelion with this volatile mix? Strong growth in coma size, driven by carbon dioxide. Early and steep increases in emission lines linked to carbon. Bearing species. A greenish appearance that can be explained with CN activity and dust scatter, even if diatomic carbon stays low. And a metal signature that rises sharply, potentially with thresholds that feel like switches only because a temperature line got crossed. None of this requires a long, rigid body. All of it is consistent with a small nucleus inside a big and lively envelope that turns on early. Could a water-poor, carbon dioxide-rich comet from another star still look very unlike anything we have seen before? Yes, our sample size for interstellar visitors is tiny. Differences that would be routine in a large sample feel shocking when you have a handful of cases. That is why we keep both doors open. A natural explanation that uses this inventory, and a more exotic one that would need even stronger evidence. Here is the handoff. The volatile story sets the stage. The next scene is metals. The data say nickel shows up and grows hard, while iron waits its turn. That pattern is older than any internet debate, and it is much harder to fake than an image color grade. If we can explain nickel without iron in a natural way inside this carbon dioxide-rich coma, the artifact camp gains ground. If we cannot, the elongated camp gets a fresh push. Time to open the spectrum lines that carry the fingerprint of metal atoms. If you have spent time around meteorites or metallurgy, you know a simple rule. Where there is nickel, there is almost always iron. They are born together in stars. They condense together in planets and asteroids. They show up together in the lab. That is why the spectra from this visitor made so many people sit up. Nickel lines appeared clearly, while iron lines hid until much closer to the sunday. The ratio looked off compared to most comets we know. So what could possibly separate these twins in a natural way? Start with temperature and partners. Metals do not simply boil off a cold surface. The energy required is huge, yet you do not always need to. vaporize the metal itself to see its signature. On Earth, there is a classic route that chemists discovered in the 19th century. Introduce carbon monoxide, let it bind to nickel at moderate temperatures. You make a volatile compound that travels as a gas. Later, it breaks apart and returns nickel to a surface. This is used to refine nickel into high-purity metal. In space, you do not have reactors. You do have carbon monoxide in the coma and on the surface. Earlier spectra told us that carbon monoxide is present. Carbon dioxide is abundant. Water is low. That is a friendly field for carbon-bearing chemistry. Could a related pathway operate on dusty grains or in micropores near the surface? It would not look like a factory. It would look like sunlight warming a mix of minerals and simple gases until a threshold is crossed. Below the threshold, nickel stays locked. Above it, nickel binds and releases. If iron sits in minerals that do not form equally volatile compounds at those temperatures, iron stays behind. Suddenly, you have a nickel signal that turns on fast while iron lags. No aliens required. Just the right inventory and a switch-like temperature response. There is a second piece that helps. The observed distance dependence for nickel production looked steep, much steeper than the usual water-driven curve. Steep curves can emerge from thresholds. Imagine the surface coated with a processed crust from long years in interstellar cold. As the object moves inward, sunlight slowly eats through that crust. For a while, nothing dramatic happens. Then a thin barrier fails, and fresh material is exposed. Rates jump. If nickel-rich phases sit just under that barrier and respond strongly to carbon monoxide, you get a surge that tracks distance with a high power. It feels like activation, but it is still thermal physics. What about iron, finally appearing inside roughly 2.5 astronomical units? That also fits a layered picture. As overall temperatures climb, minerals that hold iron start to break down, or release products that flash into the coma. The nickel-to-iron ratio then falls toward more ordinary values. This is exactly the kind of evolution you would expect if both metals are present, but trapped in different matrices with different release temperatures and different reaction partners. The early nickel dominance is the odd part. The later iron arrival is the catch-up. Skeptics of the natural pathway will point to the degree of separation. They will note that comets in our system often show nickel and iron together, even when activity ramps. That is fair. It means the burden is on the chemistry model to be specific. What minerals, what porosity, what surface renewal rates. These details matter. The good news is that they are testable. As the object moves away from the sun, the same distance trend should run in reverse. If the mechanism is thermal and chemical, nickel should decline with a similar sensitivity, and iron should fade on its own schedule. Spacecraft spectra, taken weeks apart, can watch that decay and pin down the curve. There is a geometric cross-check as well. If gas release is strongly coupled to sunlit areas, you expect directional jets. Those jets can push gently on the nucleus and alter the orbit in subtle but measurable ways. The standard comet model already solves for a small non-gravitational parameter. If the post-perihelion orbit fit requires values that match the energy implied by strong gas release, the chemistry story and the trajectory story will support each other. If the orbit requires thrust that cannot be accounted for by any plausible outgassing, the chemistry story will struggle. Could an engineered surface create the same nickel pattern? Yes, in principle. Nickel-rich coatings are common in high-temperature hardware. Heating could liberate nickel-bearing species with a steep distance dependence if protective layers thin out near a threshold. That possibility stays on the table. It just does not get to jump the line. Natural models get the first swing because they have a long track record in comet science, and they are already consistent with the volatile inventory we have seen. So where does that leave us? Nickel without early iron looks less like a smoking gun and more like a hard chemistry problem set in a carbon dioxide-rich coma. The next decisive tests are clear. Watch the metal lines evolve after perihelion. Check whether iron rises to typical ratios as temperatures fall. Compare the timing to the non-gravitational tug seen in the orbit. If the numbers line up, we have a coherent natural story. If they refuse to line up, we will give the engineered hypothesis a fair hearing in the parts ahead. Next, we widen the frame beyond chemistry. Composition is not the only weirdness. The path through the solar system has its own string of low-probability coincidences. One or two are easy to shrug off. A chain of them deserves a closer look. We will count them, and show how to think about odds without falling for narratives that outrun the data. When a story piles up coincidences, your brain starts drawing lines between dots. That is how stories work. Science asks a tougher question. Are those dots actually connected, or are we counting the hits and forgetting the misses? Before Perihelion, this visitor served up a handful of eyebrow raisers. None proves anything alone. Together, they deserve a clean look. Start with the orbital plane. The planets share a thin sheet around the Sun called the ecliptic. Interstellar objects should arrive from random directions. Most should swing through at all sorts of tilts. This one came in retrograde and only about 5 degrees off that planetary sheet. The quick back of the envelope says the chance of landing within 5 degrees by pure luck is small, on the order of 1 in a few hundred. Not impossible, uncommon enough to notice. Now stack on the flybys. The track brushed relatively near Mars in early October. It will pass near Venus in its inbound outflow. It will have a meaningful geometry with Jupiter next year. Each encounter is not a hazard. Each is still closer than you expect for a random tourist. When you multiply the odds of multiple near misses with multiple moving planets, you get a product that starts to feel small. A rough estimate puts the combined chance at the level of 1 in tens of thousands when you define near in typical ways. The exact number depends on your distance thresholds. The point is not the exact number. The point is that the stack of nears deserves attention. Add one more dot that caught the internet. Backtracing the arrival direction points to a region within single-digit degrees of a famous radio oddity from the late 1970s. No one has ever repeated that signal. Many natural and technical explanations have been proposed. Still, the proximity on the sky invites comparison. The chance of landing within that small patch by accident is under 1% by a simple area argument. You can feel the narrative gears start to turn. Path near our plane, timed flybys, a sky patch with lore. Is this design? Here is where we slow the roll. There are 2 traps that can trivialize statistics. The first is selection bias. We only notice the weird stack because we are staring at this object now. Hundreds of other plausible alignments went unremarked because no one was looking for them. The second is the look elsewhere effect. If you run many tests on any dataset, you will eventually find a low probability event by chance. That does not make it meaningful. It means you searched a lot. We can still use the odds as a guide. They tell us where to invest scarce telescope time and where to tighten models. Low probability does not mean intent, it means test harder. For example, the low tilt invites questions about the interstellar population we are sampling. Surveys are more sensitive to arrivals that spend more time near the ecliptic simply because that is where we focus many resources. That can overweight discoveries that look aligned. Retrograde also matters. A retrograde pass increases the relative speed against planetary motion. That can exaggerate perceived near-miss rates compared to a prograde arrival, because geometry changes faster. Timing is another slippery piece. The Mars near pass landed 2 days after a government pause on public communications in one country. That looks like a puzzle piece until you step back. Agency calendars and orbital mechanics are independent clocks. History is full of coincidences that feel charged even when they are just clocks colliding. So what if we take a calmer view? The stack of improbabilities says this visitor deserves maximum measurement. It does not say we know why the stack exists. The most fair stance is to treat the trajectory pattern as a flag that raises the priority of independent checks. Can outgassing explain any subtle changes in the orbit around perihelion? Do the planetary nears line up with tiny kicks that match gas physics? Are there small drifts in the light curve that line up with rotation and jets, rather than thrust? There is a story trap here. It is easy to let improbable geometry pull your attention away from the one thing that could settle the original debate. Shape. If the nucleus is compact, then the long streak lives mostly in the stack. If the nucleus is truly extended, then the geometry becomes supporting texture rather than the headline. In the next part, we return to that headline. What would a real elongated nucleus need to look like in light? What signals would it leave in images that even clever stacking cannot fake? Let us set the odds aside for a moment and go back to the photons. If the nucleus is truly long, not a trick of stacking, light should tell on it in specific ways. Nature does make stretched shapes, but she charges a price. We can check that bill with a few clean tests. The goal today is simple. Describe what a genuine, the long body would do to brightness, color, and time. Then compare those signatures to what we have. First, brightness along the long axis. A rigid, elongated nucleus presents a changing projected area as it rotates. Imagine a baton slowly tumbling. When the long side faces you, the area is large and the light jumps. When the end faces you, the area shrinks and the light drops. That creates a rhythmic light curve with a strong amplitude. If the aspect ratio is 4:1, the swing can be big. Real comets with elongated nuclei show these beats, even when a coma tries to smooth them. A smear from motion during stacking can draw a long stripe, but it will not impose a periodic heartbeat in single-frame sequences. So a decisive test is to watch short exposures over hours and look for a repeating bright, dim, bright pattern. A strong periodic signal favors a real shape over a stacking artifact. Second, width across the stripe. Time smear mostly stretches in one direction. It should not make a feature thicker than the point spread function across the motion. A true long body with a surrounding coma will be thicker than a point after convolution. You can measure the full width at half maximum across the streak and compare it to nearby stars in the same stack. If the streak is consistently wider by a non-trivial factor, that pushes away from a pure smear. If it matches the stars, stacking is the favorite. Third, limb gradients. Elongated solids tend to have sharper edges than diffuse gas. Even after convolution, their limb gradients fall off faster than a soft coma. That gives you a brightness profile with steeper shoulders near the core and softer skirts farther out. In a controlled stack that preserves linearity, you can slice the profile perpendicular to the long axis and compare to a point plus coma simulation. If the observed shoulders are too crisp for any reasonable coma model, you have a hint of genuine structure. Fourth, color zoning along the axis. In a long, nucleus scenario, the near surface can outgas from discrete vents that cluster along ridges or ends. That can create repeating color patches that ride with rotation. A smear would tend to blend these into a monotone bar unless you do object-aligned stacking, which the viral images did not. If calibrated narrowband images show color patches that repeat in time at a single period, you are watching a body, not a blur. Fifth, polarization. Light scattered by dust and gas polarizes differently depending on grain size, phase angle, and geometry. A rigid body with a thin coma can show polarization patterns that are not purely centrosymmetric. You can scan the streak with a polarimeter. If the pattern reveals a preferred orientation that tracks the stripe rather than the sun, that favors a structured source over a pure coma smear. Now anchor these tests to the Mars case. The Perseverance composite had remarkably tidy edges for a stack built from navcam frames. That tidiness raised eyebrows. However, we must remember that contrast stretching and high-pass sharpening can carve fake shoulders. Without the processing recipe, limb gradients alone are shaky evidence. The length of the stripe matched motion over about 10 minutes at the relevant speed. That supports the smear. The width across the stripe has not been published with calibration against stars from the same stack. That is a missing number. The light curve test is the most powerful and also the most underused. If we can extract a periodic signal from short navcam sequences or from ground-based tracking runs before conjunction, we would have a non-cosmetic check on shape. What about past interstellar visitors? One famous object showed a very large light curve amplitude that hinted at a high aspect ratio, or a thin pancake seen edge-on. No one had resolved images. The curve did the heavy lifting. Our case can use the same playbook. If the nucleus is genuinely long, the curve should sing. If the coma dominates and the core is small, the curve will be muted or jet-driven with irregularities that wander with activity. So, what would settle this now? Mars orbiter images at tens of kilometers per pixel could measure width and limb gradients without heavy processing. Short exposure series could reveal rotation. Narrowband sequences could map any color zoning. Polarimetry could check the scattering geometry. Each test pushes from a different angle. Together they box in the truth. If you are keeping score, the streak length still favors motion. The crispness is suggestive but not decisive without processing details. The unresolved width is a key missing metric. The absence or presence of a strong periodic light curve will likely be the tiebreaker. In the next part, we ask why these obvious checks did not arrive when everyone expected them. Mars had the best seats in the house, so where are the photos that could end this argument? If you are wondering why we still argue about a stacked rover image when Mars had full-blown orbiters overhead, You are not alone. The simple truth is that Mars had the best seats in the house. Multiple spacecraft with cameras far sharper than a rover navigation cam were in position during the closest pass. So, where are the pictures that could settle this? Let us start with what those orbiters can do. Think in plain terms. A high-resolution camera in Mars orbit can spot features on the ground only tens of centimeters across. Translate that power to a target tens of millions of kilometers away, and you still get tens of kilometers per pixel during closest approach. That is crude compared to the surface work these cameras were built for. It is still a massive upgrade over a rover navcam. On top of that, color imagers and spectrometers can split light by wavelength. That lets you separate dust scatter from gas emission and look for metal fingerprints without repainting grayscale in post. So why did a rover image leak into public hands before the best Mars? Shots did. Raw rover frames are posted by automated systems. Those pipelines run even when public affairs and many science teams are off the clock. The files arrive in a public repository with minimal processing. That is by design. It lets engineers and outside watchers keep tabs on the mission in near real time. Mars orbiter products are different. Teams plan targets. Instruments run carefully timed sequences. Data lives in mission archives. Then a chain of steps begins. Decompression, calibration, removal of known instrument quirks, cross-checks against star fields, quality control. Only after that do the images move toward public release or toward journal figures. That chain runs on people and scheduled meetings. During a government shutdown in the United States, many of those people are told not to work. Even reading work email can be restricted. That alone can add days to weeks. But here is the rub. The quiet was not only in the United States. The European spacecraft had pre-announced their observation windows. China has a history of publishing Mars material quickly for prestige. The United Arab Emirates has a public data portal and an outreach mission built into its DNA. All three had potential angles on the interstellar visitor. For several key days after the flyby, there were no teaser thumbs, no success notes, no preliminary graphics. That broad silence is why the internet spun up. It does not prove anything beyond a choice to wait. It does tell us that multiple teams decided to hold rather than drip half-baked frames into a feeding frenzy. There are good reasons for holding. If you release a single frame that looks odd without context, you risk pinning a narrative to a processing artifact. If you wait, you can bundle a set that tells a coherent story. A short exposure series to show motion and rule out smear confusion. A color set to map where green lives and where white dominates. A spectrum to anchor the chemistry. A caption that explains what you did and what you did not do. That takes time. Time is scarce when everyone is watching. There are also competitive reasons. Space science is a cooperative sport that is scored like a tournament. Teams want to publish first in peer-reviewed journals. Press releases can jeopardize novelty claims if they overshare. Reviewers ask for methods and calibration. Those pages cannot be stapled together in a night. Scientists will always trade internet applause for a rigorous paper. That does not help the public conversation in the moment. It does protect the record that will outlive the moment. So, what does that mean for us right now? It means we do not pause the investigation while we wait. We switch to what we can test with open data. That puts amateurs in the spotlight. Not because they can replace billion-dollar hardware, because they can run controlled experiments today with narrowband filters, short stacks, and careful registration. They can duplicate the smear. They can challenge the brightness profile. They can hunt for a simple rotational beat. They can publish their methods and raw frames so anyone can check. Most importantly, they can fail in public without fear and try again tomorrow. That is how you keep truth moving while institutions are quiet. One more practical point. Even if every orbiter team releases a perfect set next week, you will still want to be fluent in the basics. You will want to look at an elongated feature and immediately ask what the exposure time was and whether the growth of the streak length matches the expected motion. You will want to glance at a color image and check if it came from true narrowband filters or from a grayscale map dressed with a green palette. You will want to read a caption and see whether it specifies calibration and background subtraction. Being able to do that will save you from a dozen fake starts the next time a story like this breaks. In the next part, we turn the microphone to the Sky Army. Careful backyard. Observers produced the only sustained visual record before the sun swallowed the geometry. Some of those results are messy, some are excellent. Together, they carry clues about color, width, and short-term variability that we can weigh right now. Bring your skeptical eye and your patience. We are going to separate signal from noise without losing our sense of wonder. There is a reason I love the amateur astronomy community. When big institutions pause, backyard rigs keep humming. In September and early October, while Mars orbiters queued up and Earth telescopes were racing the sun, small teams around the world gathered photons night after night. Their images are not glossy posters. They are experiments. They are also our only continuous look before the geometry closed. What did careful amateurs actually see? The best sets share 3 traits. Short-tracked exposures that keep the moving target reasonably tight. Narrowband filters that isolate gas bands or continuum light from dust. Transparent processing notes so others can reproduce the steps. Those sets often show a white or yellowish core with a green halo that grows with time. Some frames show mild elongation even when exposure times are short enough to limit motion blur. That is interesting. Not a verdict. Interesting. Now, the messy side. Viral posts mashed aggressive sharpening on top of stretched contrast. High-pass filters can carve artificial edges and turn a soft blur into a bar with crisp shoulders. Deconvolution can amplify noise and paint tiny speckles into fake structure. Colorized grayscale can trick your eye into thinking gas is present when the palette is simply a choice. A few clips that made waves were not telescopic data at all. They were AI renders spliced into threads with confident captions. If you remember one rule from this part, make it this one. Always ask to see the raw stack and the exact steps between raw and final. Here is how the stronger amateur groups worked. First, they verified the ephemeris and tracked on the comet rather than the stars. That kept the core as a compact smudge in each short frame. Next, they shot 3 sequences, one through a filter centered on classic green emission, one through a filter that sits on the blue-violet band where CN contributes, one through a continuum filter that dodges emission and captures dust scatter. Then they stacked each sequence separately in short windows. 90 seconds, 2 minutes, 5 minutes. They measured the width across the core in pixels and compared that width to nearby stars from the same frames. They plotted brightness over time to hunt for a simple repeating beat that would hint at rotation. What emerges from those careful runs? The green halo is real in several data sets. It thickens as activity rises. The core stays white in the continuum stack, which means reflected light from dust and a compact central source still dominate the center. The width across the best short stacks is only slightly larger than stars, which is consistent with a compact source wrapped in a thin coma. Some observers report a weak periodic brightening on the scale of hours. Others see no clean rhythm because the signal is faint and the atmosphere adds jitter. That is honest science. Some nights you get coherence, some nights you get weather. There is a neat trick the community can deploy more widely: time slicing. Stack the first 10 minutes, then the next 10, then the next. If the elongation grows directly with the window length while the width stays constant, you are watching a smear. If width grows faster than you expect from the point spread, you may be catching real structure bleeding beyond the core. Combine that with filter splits, and you can map where gas dominates versus where dust carries the light. Quality control matters. A proper post should include the telescope aperture, focal length, camera model, pixel scale, exposure time per frame, number of frames stacked, registration method, and any sharpening or deconvolution parameters. It should include at least one raw sub and a minimally stretched stack for comparison. When posters share that level of detail, the community can replay the work and check the claims. When they do not, treat the image as a sketch, not as a measurement. So what do we take forward? The amateur record supports a green coma that intensifies through September. It supports a central region that is bright in continuum light and therefore stubbornly white in many processed composites. It hints at mild elongation in some short stacks, but the evidence is not uniform and not yet periodic in a way that would scream long, rigid body. That keeps both main explanations alive while we wait for higher resolution frames. The best part is the culture. Thousands of people tried, failed, learned, and tried again. That is how you turn a viral mystery into a classroom that spans the planet. In the next part, we pivot from the ground to the clock in the sky. Perihelion is a stress test. It turns up the heat, it turns on chemistry, and it makes small differences grow. Earth is about to lose direct line of sight. Spacecraft will see part of the show. The question is simple. What should happen if this is a natural comet with odd chemistry? What should happen if it is not? Let us set the expectations now so we can judge the result fairly. Perihelion is the moment when the sun turns the volume knob to max. For any comet, this is where the physics gets loud. For our visitor, it is where small clues can become big tells. We need a clear scoreboard before the heat hits, because Earth is about to be blind for a few crucial weeks, and only a handful of spacecraft will have any kind of view. Let us lay out the geometry. From Earth, the object slides too close to the sun on the sky. The glare swamps our telescopes. Even space observatories near Earth lose the target until it reappears on the far side. A few solar watching missions can see around the edges. A coronagraph can block the sun and show faint surroundings, but its resolution is coarse, and its cameras are tuned for the solar wind. They can catch a brightening and a tail, but they will not draw a crisp outline of a small nucleus. A solar probe can image the inner heliosphere with better detail, yet its imaging windows and angles are not optimized for a fast-moving interstellar target. The best detailed look is scheduled later, when a Jupiter-bound spacecraft has the right line of sight in early November. That timing matters. It means the exact moment of maximum heat may pass without a clean, high-resolution portrait. So, we use prediction to turn limited data into a test. If the object is a natural comet with odd chemistry, expect a few things. Activity should climb as sunlight increases. Carbon dioxide and carbon monoxide should drive early gas release. The coma should expand. The greenish hue can intensify in gas bands even if diatomic carbon stays low, because CN and dust scattering can still carry the color. Metal lines should grow rapidly as thresholds are crossed. Nickel can spike due to favorable chemistry in a carbon-rich environment, while iron lags until the surface warms further. The overall light curve should brighten smoothly, with short-term jitters from jets. Fragmentation is on the table if internal cohesion is weak. A break would likely produce multiple condensations and a temporary surge in brightness as fresh surfaces are exposed. Orbit-wise, natural jets can introduce a small non-gravitational push. That shows up as a gentle tweak to the best fit trajectory once the object reappears and the fits are updated. If the object is not a standard comet, what would look different? Survival through perihelion without fragmentation is not decisive by itself, since many natural comets also survive. Look instead for patterns that feel like switches rather than curves. A steep metal emission rise is already expected, but an abrupt plateau or a step change, at a distance where no plausible volatile threshold sits, would be suspicious. A persistent, smooth light curve with very low short-term jitter could hint at a coherent surface that is not venting from many random patches. An orbit change that exceeds the momentum available from any reasonable outgassing budget would force us to consider non-natural thrust. None of these alone would prove intent. Together they would demand a different conversation. Now the practical issue. During the weeks around perihelion, your feed will be full of dramatic frames. Coronagraph images make comets look like ghosts in a storm. Process stills from solar images can exaggerate tails and halos. Remember what those instruments are designed to do. They are excellent for watching solar wind structures and coronal mass ejections. They are not microscopes for tiny nuclei. Treat any claimed shape from those cameras as suggestive only. Use them for timing of outbursts and for broad trends in brightness and tail direction. What can we measure cleanly while Earth is blind? Total brightness in the coronagraph field, tail development and orientation, any obvious outburst that changes magnitude by a large step. If there is a breakup, even a coarse instrument should show multiple condensations moving apart. If nothing dramatic happens, the quiet is data too. It sets upper bounds on turbulence in the light curve and on how wild the outgassing became at peak heat. Here is our promise to you. We will not call a winner during the blind window. We will write down every prediction we just made, and then we will grade them when ground-based telescopes regain the target in December. If you want to play along, write your own prediction in the comments right now. Brightens smoothly. Fragments. Nickel and CN spike hard. Orbit unchanged within natural limits. Pick your 4 boxes, and we will check them together. In the next part, we take the prediction game one level deeper. We ask what the physics says about maximum heat for this particular inventory, how carbon dioxide, carbon monoxide, and a dash of water can combine to create steep curves that look like triggers even when no one is pressing a button. When you see an apparent switch at perihelion, You need to know whether the switch is chemistry or design. Time to let the equations speak in plain language. When the sun turns up the heat, physics gets very specific. You do not need exotic ideas to get dramatic behavior. You need sunlight per square meter, a surface that absorbs it, and materials that decide to turn solid into gas once a threshold is crossed. The art is translating that simple picture into what you would actually see from millions of kilometers away. Start with the energy budget. At 1 astronomical unit, the solar constant is about 1360 watts per square meter. At a distance of roughly 1.4 astronomical units, which is near this perihelion, the flux drops to about 700 watts per square meter. That is still a lot for a surface that has spent eons near cosmic night. A dark crust absorbs a fraction of that power. Some is re-radiated as heat, some conducts inward. Some goes directly into breaking molecules free. That last part is sublimation. It is the engine of every coma. Different ices answer the sun at different temperatures. Carbon dioxide wakes up earlier than water. Carbon monoxide can appear even earlier if it is trapped shallow. Each volatile adds a switch-like behavior to the curve of activity versus distance. The Hertz-Knudsen relation tells you how many molecules leave the surface per unit area as a function of temperature and vapor pressure. You do not need to write the equation here. Just know it rises very fast once the temperature sneaks past a critical zone. That steepness is why a plot of production rate versus distance can look like a power law with a big exponent. It feels like someone flipped a switch. In reality, the surface simply warmed, enough to hop a chemical fence. Thermal skin depth is the next lever. Sunlight does not heat to infinity. It warms only a thin layer over the course of a rotation. If the rotation is hours long, the daily wave of heat might only reach millimeters to centimeters deep. Below that, temperatures lag. A crust just a few millimeters thick can act like a valve. For days, nothing dramatic happens. Then a crack opens or the conductive path thins, and hidden volatiles touch the warm zone. The visible activity surges. Again, no intent is needed. The geometry of pores and fractures and grains can create the on-off feeling by itself. Now imagine a nucleus that rotates with a period of a few hours. Sunlight sweeps across active patches. Vents point toward the sun and then away. This creates time structure in the outgassing. A light curve can show jitter on hour scales as jets turn on and off with rotation. If the object is a natural comet with many small vents, you expect the brightness to wander with a noisy rhythm during maximum heat. If instead you see a very smooth and almost perfectly monotonic curve with minimal short-term jitter, that would be unusual for a rubble pile with patchy activity. Not impossible, unusual enough to flag. Fragmentation is the loudest natural outcome near perihelion. As heat penetrates, gases trapped in voids build pressure. Weak materials can fail. The nucleus can crack or split. This is common in comets that lack cohesion. The signature is a sudden brightening as fresh ice is exposed, followed by the appearance of multiple condensations that separate slowly. You can also see kinks in the tail as dust release spikes. If fragmentation appears, the scale tips toward a natural nucleus that could not handle the stress. That is one of the cleanest discriminants you can hope for. Outgassing does more than glow. It pushes. Each molecule that leaves the surface carries momentum. If more gas leaves on the sunward side than on the night side, the net force acts like a tiny thruster. Orbit fitters parameterize that effect with coefficients that scale with activity. During and after perihelion, you can measure how much the path bent compared to a purely gravitational prediction. If the deviation is consistent with the energy carried by realistic gas production, physics is happy. If the deviation would require absurd mass loss to explain, then something is wrong with your assumptions. Either the outgassing is wildly asymmetric in a way that leaves additional fingerprints, or an extra source of momentum is present. Metals join the party through chemistry, not heat alone. Nickel lines can rise steeply if the surface enters a temperature and gas environment that favors volatile complexes. Iron can remain quiet until different minerals reach their own thresholds. The key is continuity. If nickel climbs before perihelion, it should ease in a mirror-like way after perihelion, as the energy budget retreats. Sudden steps with no matching thermal story would be strange. Gradual arcs with hysteresis, where sunlit history matters, would be normal. So the prediction ledger for a natural comet at maximum heat looks like this. Rapid growth of gas and dust, a bright coma that expands, a light curve with short-term noise from jets and rotation, possible fragmentation if cohesion is poor, a small but measurable tweak to the orbit that scales with activity, a metal story that ramps and then settles with distance. None of those signs prove nature. Together they define a natural baseline that we can grade against the real data. In the next part, we will try on a different hat. Suppose someone wanted a probe to look like a comet during a perihelion pass. What coatings would they choose? How would threshold exposure to sunlight turn on emissions without a rubble pile beneath? Could a designed shell survive heat with a smooth light curve while still venting enough gas to look comet-like? We will treat that as a thought experiment to keep our reasoning honest. Take a breath and imagine a design brief. Build a probe that must cross interstellar space for ages. It has to survive radiation, dust hits, and deep cold. Then it must pass near a star where heat and light spike. The probe must look natural to any curious species with telescopes. If that is the task, what would you coat it with, and what signatures would that design leave in our instruments? Start with the disguise. If a craft wants to masquerade as a comet, it needs volatiles that wake up at the right distances. Carbon dioxide is a prime candidate. It is common in space. It sublimates at relatively low temperatures compared to water. It produces a bright coma early and can carry a greenish tint when other carbon fragments are present. Add a smaller inventory of carbon monoxide. CO is even more volatile and reacts readily in environments with metals and sunlight. A thin layer of CO and CO2 ices embedded in a dust matrix could form a controllable skin. When sunlight rises above a threshold, vents open and gas boils off. Observers see a coma and a short tail. The core stays visually compact if the structural shell beneath is rigid. Now, consider the skeleton under the skin. Long-life hardware tends to use alloys that do not crumble under heat and radiation. Nickel-rich alloys are a workhorse class in engines and space structures. They resist corrosion. They hold strength at high temperature. Some are plated to stabilize surfaces. If such a shell spent eons collecting interstellar grime, it could arrive in our system wrapped in an insulating crust. As the sun warms the crust, volatile films and adsorbed compounds desorb. At a critical point, hotspots expose parts of the metal shell. Nickel-bearing species outgas. That would raise nickel emission lines steeply as distance falls. Iron lines could lag if the surface chemistry and mineral phases prefer nickel release under those conditions. This is not a claim. It is a consistent picture that uses as known materials. What about the white core and green edges that sparked so much debate? A designed shell with a bright reflective surface under a thin, volatile layer could produce a white-dominated center in stacked images, while a greenish gas halo wraps the sides. If vents concentrate along a sunlit belt, a sunward plume can appear. Observers sometimes call such features anti-tails depending on geometry. The plume can look like a forward extension, not just a trailing tail pushed away by solar wind. Natural comets can do that in some geometries too. The difference is in the regularity and stability of the feature as heat increases. Light curves offer another test. A rubble pile with patchy jets tends to jitter on hour scales as vents rotate in and out of sunlight. A rigid engineered shell with a modest number of controlled vents could ride perihelion with a smoother profile. Not perfectly smooth, just unusually calm compared to an object with dozens of random pores and cracks. If you chart brightness during maximum heat and see minimal short-term noise while gas output remains high, the design scenario earns attention. If you see noisy flicker that tracks rotation, the natural scenario gets the nod. Could such a craft change its path at perihelion? Physics says that if you want the most change in energy for a given thrust, you fire at fastest speed. That point is near perihelion, where velocity peaks. A small propulsive event buried inside the glare could alter a hyperbolic path into a long-bound arc. Natural outgassing can also push. The discriminant is accounting. You estimate the momentum in the gas from measured production rates and speeds. You compute the orbit change that gas could cause. If the observed change exceeds that budget by a wide margin, you are missing something. It could still be natural if jets are wildly asymmetric in a very specific way. If no plausible jet geometry carries the day, the conversation moves. There is a counterpoint you must hold in mind. Natural chemistry can mimic many of these signatures. Thresholds in sublimation can look like switches. A sunward plume can arise from dust sheet dynamics. Nickel without early iron can emerge from carbon monoxide-assisted pathways if the minerals line up just so. A smooth light curve can happen if activity concentrates into a few vents. The right rubble pile can walk and talk like a design without any intent inside. So why entertain the disguise at all? Because there is value in building a model that makes clear predictions. A disguise model predicts early CO, 2-driven coma, steep nickel activation near a surface exposure threshold, unusually smooth brightness at peak heat, and possibly a post-perihelion trajectory change that cannot be paid for by gas. A natural model predicts a similar coma, steep chemistry tied to thermal thresholds, measurable hour-scale jitter, and a trajectory change that matches an outgassing budget. The overlap is large. The separation lives in the details and in the accounting. Here is the promise. We will not crown a theory because it is exciting. We will keep the engineered hypothesis on the table only if data refuses to sit comfortably inside natural explanations. In the next part, we take a breath and do statistics without drama. How often should an interstellar visitor happen to line up with our planetary plane and graze multiple worlds? How easy is it to fool ourselves by spotlighting surprising patterns while ignoring all the ordinary passes? We will turn the math into intuition so you can feel the odds in your gut before we return to post-perihelion orbit fits. Statistics can feel like magic or like a trap. The same numbers that reveal patterns can also seduce us into seeing design where there is none. Our job in this part is to turn space odds into gut-level intuition. We will take the 3 eye-catchers people quote most often: the low tilt near the ecliptic, the string of planetary near-passes, the sky patch that brushes against an old radio mystery. Then we will rebuild the math with simple mental models and the 2 classic warnings, selection bias and the look elsewhere effect. Begin with the ecliptic. Picture the solar system as a thin disk with a fuzzy thickness. Planets orbit inside that sheet. If interstellar objects arrive from random directions, only a small fraction should cross within a few degrees of the disk. If you draw a band 5 degrees tall around a sphere, the area of that band is small compared to the whole. The back of the envelope puts the chance at roughly 1 in a few hundred for a random arrival to sit that close. That sounds special. Now add detection bias. Our surveys spend more time near the ecliptic because that is where most targets live. Telescopes and observation schedules follow the plane. That means we are more likely to find passers-by that happen to be near the plane. The true odds of discovering a low-tilt visitor can be way higher than the raw geometric fraction suggests. The event feels rare. The observation pipeline makes it less rare. Now, stack the flybys. Imagine throwing pebbles through a solar system model where planets are marbles moving on rings. Most pebbles miss all marbles by wide margins. A few pass within a marble length. Fewer still skirt 2 or 3. When you hear that a path grazes Mars, then later Venus, then lines up for a meaningful geometry with Jupiter next year, it sounds like a plan. But geometry and timing team up. Planetary orbits are crowded in the inner system. Windows for near passes open, surprisingly often, when you allow a wide range of distances to count as near. Multiply the chances, and you still get a small number. You must also multiply by a large look elsewhere factor because you would have noticed any other interesting pattern. Earth plus Mars, Venus plus Mercury, Jupiter plus Saturn. If you search many pairs and triplets, you will eventually find a path that seems uncanny. The right way to feel these odds is not awe or dismissal. It is curiosity with caution. What about the arrival direction nudging toward an old radio puzzle? The sky is big. The region you can reasonably call near that old signal is not huge, but it is not a point either. A random path landing within several degrees is unlikely on a single throw. Across many random throws, the chance of at least one landing near an interesting spot rises fast, especially when many sky spots are interesting. Pulsars, galaxies, star-forming regions, cold gas clouds. If you run enough comparisons, you will find a short separation somewhere, and it will feel like fate. There is a better way to let odds guide you without letting them lead you. Treat probabilities like weights on a scale rather than like verdicts. A stack of unusual alignments makes it more rational to spend telescope time and careful modeling on this case. It does not make it rational to jump to intentional design. Bayesian thinking helps here. Start with a very low prior for an engineered object. Update that prior as oddities appear. Each oddity should nudge the probability, but cannot by itself change a tiny prior into a large one. Only direct evidence can do that. A resolved structure, a thrust that is impossible to pay for with gas, a signal that repeats in a way that matches a mechanically meaningful rotation rather than a jet blink. You can also lean on simulations. Monte Carlo experiments throw millions of synthetic interstellar tracks across a digital solar system. They count how often paths pass within given distances of planets and how often the tilt lands near the ecliptic. They include the sensitivity map of real surveys. Those experiments routinely recover clusters of chance alignments that look story-worthy. That does not make our case uninteresting. It places our case inside a broader distribution where odd stacks do occur. The real test is still ahead, and it is beautifully concrete. After perihelion, we will measure the path again. If any deviation from a gravity-only path fits the energy carried by natural outgassing, then the orbit sits comfortably inside. Chance plus physics. If the deviation demands momentum that outgassing cannot supply, the odds flip from a story about discovery bias to a story about missing forces. In the next part, we will define that test cleanly. How to check the track after the Sunday. How to turn tiny position changes into a verdict about gas versus something more. When the object swings past the sun and peeks back into a darker sky, the cleanest test begins. We stop arguing about pixel aesthetics and start measuring gravity. The question is simple. Did the path change in a way that natural outgassing can explain? If yes, case mostly closed. If no, the debate levels up. Here is how orbit fitting works in plain language. Before conjunction, you have a set of precise positions on the sky, measured at known times. Each point says the object was here at this moment. Feed those positions into a solver that knows the gravitational pull from the sun and the planets. The solver returns an orbit that best passes through all points. For a comet, you also allow a small extra push called a non-gravitational term. This term stands in for the net thrust from outgassing that tends to be stronger on the sunward side of the nucleus. That thrust is weak compared to gravity, but over weeks it adds up. After conjunction, you take new positions and run the solver again. If the same orbit plus a reasonable non-gravitational term still matches, the physics is happy. Reasonable means the implied mass loss and jet geometry are in line with what spectra and brightness suggest. If the solver demands a much larger extra push than the coma can plausibly provide, something is wrong. Either the jets were outrageously asymmetric, or the model needs another source of momentum. The calculation is not mysterious. Outgassing carries momentum equal to mass flow times exhaust speed. Spectra and photometry tell you the mass flow within a factor of a few. Gas speeds are also known within ranges for common molecules. Multiply those, and you get a thrust budget. Compare that budget to the trajectory change. If the required impulse is bigger than the budget by an order of magnitude, natural jets cannot pay the bill. There are details that matter. The direction of the non-gravitational push should roughly line up with the sun if sunlight is the driver. Deviations can occur if active vents sit off-center, or if rotation modulates which side vents most. Still, the average thrust vector over weeks should not wander randomly. Fitters check that too. They look for smooth behavior in the extra term as distance changes. A wild jump in the fitted parameter with no matching change in activity would be suspect. Light curves help cross-check the dynamics. If the brightness shows strong hour-scale jitter from rotating jets, you expect the non-gravitational term to wiggle gently with the rotation period when you fit dense datasets. If the light curve is quiet and the fitted push is huge, the story does not cohere. Conversely, a noisy light curve with a modest push is a comfortable, natural combination. What does the observing plan look like once the object reappears? First, you want a dense cadence of astrometric measurements from many observatories across longitudes. That gives you frequent position updates and helps average down local atmospheric errors. Next, you want spectra to keep tabs on production rates. If nickel and CN stay high, the mass flow is large and the push can be stronger. If activity fades quickly while the fitted push remains high, you have a mismatch. You also want short exposure images to probe for any fragmentation that could shift the center of light relative to the center of mass and mimic a trajectory change. If the nucleus split, the photocenter can drift in ways that look like thrust unless you model the pieces. There is one more subtlety: solar radiation. Pressure pushes on dust grains in the coma and tail. For small grains, the effect is non-negligible, but radiation pressure acts on the dust. not on the massive nucleus. It can bend tails and change the appearance of the coma without moving the nucleus much. Astrometric pipelines are careful to measure the position of the central condensation where the nucleus sits. That keeps dust pressure from contaminating the orbit solution. It is still wise to check that your centroiding is not biased by an asymmetric tail. Observers can rotate the detector or change filters to ensure the measured position is robust. A quick reassurance about hazard. Even a measurable non-gravitational term does not imply danger. The distances involved are vast, and the geometry does not intersect Earth. Orbit solutions are updated continuously. If anything unusual appeared, the professional community would see it quickly and report it. You can be curious without being worried. While these measurements roll in, your feed will fill with hot takes. Some will claim giant course changes from low-resolution images. Others will dismiss any deviation as data noise. Neither extreme helps. The best stance is patient curiosity, anchored to the fit reports from recognized orbit computers and the Minor Planet Center. Those pages will publish revised elements with uncertainties. You will be able to see whether the hyperbolic excess speed changed meaningfully, whether the eccentricity moved toward a bound orbit, and whether the non-gravitational term stayed within the range seen in active comets. Here is how you can follow along like a pro. When a new solution posts, look for 3 items: the residuals between observations and the model, the magnitude and direction of the non-gravitational parameter, the reported uncertainties. Small residuals and a modest sunward-directed term are the natural signature. Large residuals that shrink only when the extra term spikes far beyond what the spectra suggest would be a red flag. In the next part, we step away from telescopes for a moment and talk about you. Big mysteries attract noise. To navigate the next few weeks, you will need a simple toolkit for sorting signal from hype on the internet. We will give you that kit and a checklist you can apply in minutes, so you can be a calm skeptic while everyone else is refreshing their feeds. When a space story heats up, the online world becomes a maze. Hot takes outrun data. Confident threads drown out careful updates. You do not need a lab to stay grounded. You need a simple checklist and the habit of saying the 3 most powerful words in science. I do not know. Here is how to move through the next wave of posts without losing your curiosity or your time. First, source. Ask who is speaking and what they can actually see. A mission account with a track record of calibrated releases carries weight. An observer who posts raw frames with timestamps and gear details is valuable. An account that only posts cropped images with dramatic labels and no method is entertainment. It is not evidence. If a claim does not link to primary data, park it. Second, method. Good posts tell you what telescope, focal length, camera, pixel scale, exposure time, number of frames, registration approach, filters, and processing steps were used. They include at least 1 raw sub and a minimally stretched stack. If you cannot see the pipeline, assume the picture is an illustration. That includes pretty color palettes pasted on grayscale. A green look is not the same as a green emission line. Without narrowband confirmation, a colorized image is a poster, not a measurement. Third, motion. Elongation in a stacked image is meaningless unless you know the integration window. A smear should grow in length with longer stacks, while width stays near the point spread. Ask to see time slices. 10 minutes stacked, then 3 minutes, then single frames. If length scales with window, while width does not, you are looking at motion integrated into shape. If width grows strangely, there might be processing or real structure. Either way, you learn something. Fourth, comparison. Every image that claims a new feature should include a cutout of a nearby star and a notation of full width at half maximum. Streaks that are wider than field stars by a clean factor can be interesting. Streaks that match star widths are standard smears. If the post does not show comparisons, make the request in the comments. Civil pressure improves community standards. Fifth, context. An individual spectrum or light curve is a snapshot. Look for trends across days. Steep rises followed by mirror-like declines point to thermal thresholds, which are natural. Abrupt steps with no matching change in geometry or solar distance deserve a second look. If a post shows a spike, ask for the sequence before and after. No sequence, no story. Sixth, language. Responsible posts use verbs like appears, suggests, and is consistent with. Irresponsible posts use declares, Proves and exposes. Pay attention to hedging. Good hedging is not weakness. It is a marker that the author respects uncertainty. If a post mocks caution and promises revelation, you can safely scroll on. 7th, duplication. A real phenomenon will show up in independent datasets. If only one person on Earth can see a dramatic shape, the odds are high that it is processing or equipment specific. Encourage replication. Share observing plans. If 2 or 3 observers at different sites reproduce a weak rotational beat or the same width excess under similar filters, your confidence can rise. 8th, accounting. Claims of a dramatic orbit change must be paid for with momentum. Ask whether the poster estimated the thrust from measured gas production. Ask whether they compared that thrust to the observed deviation reported by orbit fitters. If there is no accounting, the claim is a story, not a result. 9th, timeline. Perihelion and conjunction create genuine data gaps. In those gaps, speculation inflates. You can set a reminder for the dates when spacecraft post archives are likely to refresh and when ground telescopes regain access. During gaps, practice doing nothing. That is a skill. Curiosity can wait for truth. Finally, community. Use your power kindly. In the comments, ask for raw frames. Ask for calibration details. Thank people who share methods. Ignore bait. Invite viewers who are new to astronomy to try a simple analysis like time slicing or star width comparison. When you elevate method, you raise the waterline for everyone. If you find this guide useful, drop a short note below and share one tip you use to vet a viral claim. Your playbook might help thousands of other curious minds this week. We will pin the best tips so the thread becomes a live resource. Now that your skeptic toolkit is sharpened, we return to the lab bench. New spectra will arrive as the object swings away from the sunday. Those lines will tell us whether nickel keeps leading iron, whether CN carries the green, and whether the thermal story stays coherent. Fresh chemistry is coming. In the next part, we set up exactly how to read it so that when the plots appear, you can pull meaning from them in minutes. Spectra look like barcodes to most people. To a comet watcher, they are diaries. Every line is a sentence about what molecules are awake, how fast the coma is breathing, and whether metals are joining the party. In this part, we set you up to read those diaries yourself. When new plots arrive, you will be able to pull meaning from them in minutes. Start with the cast of characters. CN sits in the blue and violet. C2 paints classic green bands. CO2 usually shows up by its daughter products and by infrared features from space-based instruments. CO rides with it in the carbon family. H2O leaves fingerprints in the infrared and through daughter species like OH in the ultraviolet. Metals such as nickel and iron appear as narrow, lines at specific visible wavelengths. Remember the core puzzle. Earlier work suggested a coma heavy in carbon dioxide and carbon monoxide, lean on water, with nickel turning up before iron, and a green look that could not be blamed on strong C2. Your job is to see whether the post-perihelion spectra continue that story or swing towards something more ordinary. Rule 1 is subtraction. Comets shine both by emission from gas and by sunlight reflected off dust. To isolate gas, you subtract the continuum. Good plots will show a raw spectrum and a continuum-removed version. If a post only shows a neon-looking trace with peaks and no baseline, ask to see the continuum step. Without it, a bump can be dust color masquerading as gas. With it, a spike means real emission. Rule 2 is ratios. Absolute brightness depends on telescope size, exposure, and sky. Ratios between lines are far more portable. CN to C2 tells you whether the green you see is classic or alternative. CO or CO, 2 proxies to H2O, tells you which volatile is running the show. Nickel to iron tells you whether the early metal imbalance is easing. A natural baseline says CN can be strong even when C2 is weak, if carbon chains are depleted. Nickel should peak near perihelion and then relax while iron grows late and then fades on its own curve. If nickel stays huge and iron stays low long after heat declines, that is odd and worth attention. Rule 3 is the distance trend. Production rates plotted against heliocentric distance should climb steeply as the object approaches the sun and then decline as it moves away. The slope can be very steep because sublimation has thresholds. If you see a clean power law before perihelion, look for a mirror image after. Some hysteresis is normal because surfaces change. A step that appears with no matching temperature story is not normal. Look for continuity first before you let your imagination run. Rule 4 is line shape. Emission features have widths, thermal motion, and expansion speeds broaden lines. Rotation can add slight asymmetries. Instrumental resolution smooths everything. A narrow metal line that stays narrow and centered tells you the atoms come from a calm coma. A line that widens or shifts can indicate stronger outflow or jets. If post-perihelion lines narrow and dim smoothly, that is a natural retreat. If they spike or shift in ways that decouple from other gases, ask why. Rule 5 is aperture and geometry. Spectrographs use slits or fibers that capture light from a specific patch of the coma. A small aperture near the core samples fresh gas. A larger aperture mixes in older, more diluted material. Honest papers report the projected kilometers sampled at the comet, along with the slit orientation relative to the Sunday. When comparing two spectra, check that the apertures are comparable. If not, differences can be geometry, not physics. Rule 6 is calibration. Good teams observe standard stars the same night to correct for instrument response. They subtract skylines. They report uncertainties. If a plot lacks error bars, be cautious. Emission near the noise floor can look like a discovery when it is a fluctuation. Error bars will tell you whether a small rise means anything. Now the checklist for the metals. Look for the nickel line intensities as a function of distance. Do they follow a steep curve into perihelion and then back down after? Does iron appear later and then fade? Do the nickel to iron ratios drift toward values seen in ordinary comets as the object cools? If yes, you have a coherent thermal and chemical story. If nickel remains dominant with no natural pathway to keep it so, the chemistry model needs revision or an extra source must be considered. Finally, tie the spectrum to the dynamics. Spectra give you a gas production rate. Multiply by a typical outflow speed, and you get momentum per second. Integrate over time to estimate the total impulse available to push the nucleus. Keep that number in your back pocket when orbit updates appear. If the fitted non-gravitational term demands more momentum than the spectra can supply, that mismatch is where serious questions begin. Here is your action. When the next spectral plot hits your feed, pause before reading the caption. Identify the continuum. Note CN, C2, nickel, and iron. Scan for ratios. Glance at the reported distance. Ask how big the aperture was. Then read the caption and see if your quick take matches the author's. Post your reading in the comments and compare with others. You will be surprised how quickly you become fluent. In the next part, we step into politics for a careful minute, not to pick sides. To understand why statements from agencies and officials sounded cautious and why that caution can be perfectly normal when data are still moving. Then, we march straight back to evidence. If you listened closely to the public statements in early October, you heard a very particular tone. Calm, non-committal, heavy on reassurance, light on specifics. That style frustrated people who wanted a headline. It also fits how responsible institutions talk when data are ambiguous and reputations ride on getting the first paragraph right. Start with the obvious constraint. Many American civil servants could not speak at all because their agencies were partially shut down. Even when spacecraft keep flying, communication shops and many science pipelines do not. Outside the United States, teams were still active, yet even active teams often avoid definitive statements during a fast-moving observation campaign. They would rather wait for calibrated sets than issue a sentence that will need walking back 2 days later. That is not drama. That is muscle memory from 1,000 paper reviews. There is a second constraint that is less visible. Space missions are consortia. Cameras and spectrometers belong to international teams, with publication plans years in the making. When something unexpected appears, those teams coordinate to avoid stepping on each other. They schedule joint releases. They harmonize language so that figures and captions tell one story rather than several competing ones. Coordination slows speed. It increases clarity. In a viral week, that trade feels painful. In the long run, it prevents confusion that can take months to unwind. Then there is the risk calculation. If an agency speculates, and the speculation later proves wrong, trust suffers. If an agency undersells and later upsells, trust survives. That asymmetry pushes cautious phrasing. You heard words like monitoring and evaluating and no known hazard. Those are not evasions. They are placeholders that signal two things. First, teams are looking. Second, no one has seen a danger that demands immediate public action. That last piece matters because it lets you relax about safety while staying curious about the science. Political attention does not always mean secrecy. High visibility can simply reflect that a story has crossed from the science section into the general news cycle. Elected officials get asked, so they ask agencies for status. If you are an official and you have one paragraph to give the public, you choose the version that will still be true next week. That is why you heard acknowledgements without claims. Appropriate agencies are monitoring is bureaucratic on purpose. It protects the next update from the trap of contradicting the last. There is also protocol around extraordinary claims. Astronomers have rough norms for potential detections that would change the story of our place in the universe. Verify with independent data. Share methods. Wait for peer review when possible. Avoid unilateral declarations. The same culture bleeds into how agencies talk about ambiguous evidence that could be read as unusual. This is less about hiding and more about not lighting a fuse before you know where it runs. So what should you expect from official channels over the coming weeks? A slow cadence of carefully framed posts, images with captions that emphasize exposure times, calibration, and uncertainty, plots that prefer ranges over single numbers, statements that remind you which interpretations are consistent and which are not supported. If you want drama, social feeds will supply it. If you want the foundation that historians and students will still cite a decade from now, you will find it in those careful paragraphs and in the papers they point to. Your role as a viewer is simple and powerful. Reward the careful posts with attention. Share the ones that include raw frames or links to archives. Quote the sentences that explain what is unknown. Ask questions that make room for a later answer, rather than pin a team to a premature stance. If you do that, you nudge the ecosystem toward better habits. Enough civics. The next steps are scientific and specific. We're about to enter the phase where early post-perihelion data trickle in. First will be low-resolution solar images with brightness trends, then targeted spectra. Then the sharper views from deep space missions that were well placed for November. After that, ground telescopes get their turn. In the next part, we write a simple scoring card that converts those drops into points for each side of the debate. It will let you track the story without waiting for anyone to summarize it for you. A good mystery needs a scoreboard, not to crown a winner by vibe, but to keep us honest as new data arrive. Our case has two live explanations: a natural comet with unusual chemistry, a designed object wearing a comet costume. Both predict overlapping behavior. The separation lives in details that you can track yourself. Here is a simple way to count points as the sky starts talking again. Begin with brightness over time. Pull the light curve from the solar images and from any early deep space cameras. Ask one question. Does the brightness climb and fall along a smooth arc with small jitter superimposed? If yes, that is natural flavored. In a rubble pile with many small vents, rotation and jet patchiness create short-term wiggles. If the curve is almost perfectly smooth for days during maximum heat while activity is high, put a small mark in the design column. The mark is small because a few large vents on a natural nucleus can also smooth the curve. Next is fragmentation. Scan the coronagraph frames and the first resolved images after perihelion. Do you see the single central condensation split into two or more persistent condensations that drift apart with time? If yes, place a large point in the natural column. Breakups near maximum heat are a classic comet behavior when internal cohesion is poor. If the object sails through with no sign of cracks, do not award any automatic points to the design column. Many natural comets also survive intact. Lack of fragmentation is neutral unless other items line up. Now, metals. When the first spectra after perihelion appear, look for continuity and symmetry. Nickel should rise steeply into perihelion, then fall in a similar way as the object moves away. Iron should lag and then fade on its own schedule. If nickel remains high while iron stays stubbornly low even as the energy budget declines, and if that plateau resists all reasonable thermal and mineral explanations, give a medium point to the design column. If both metals behave like temperature stories with threshold flavor, give a medium point to the natural column. Color, next. Narrowband images that isolate CN and C2 will tell you whether the green halo is coming from the usual suspect or from an alternative. If CN dominates while C2 remains low and the green look still appears, that supports the earlier composition story and leans natural. If the halo stubbornly looks green in broadband images but narrows down to white when you isolate gas bands, that means palettes fooled people and the smear debate loses fuel. Offer a small natural point for clarity and move on. Geometry follows. Measure the width across the central stripe in short stacks and compare to stars in the same frames. If the width is only slightly larger than stars, that points to a compact core wrapped in a thin coma. Put a small point in the natural column. If the width is consistently larger across many clean datasets, and the limb gradients are sharper than any point plus coma model can reproduce, give a medium point to the design column. Remember to demand processing notes before you award anything. The non-gravitational push is the anchor test. When the orbit solvers post updates, compare the fitted extra thrust to the momentum that the spectra say the coma can supply. If the push is modest, roughly sunward on average, and the momentum fits within the gas budget, award a large point to the natural column. If the push is large, poorly aligned with sunlight, or requires far more momentum than outgassing can deliver, award a large point to the design column. This item should weigh more than any single image debate, because it ties chemistry to mechanics. Rotation comes next. Short exposure series from capable cameras can reveal a repeating bright dim rhythm. A strong periodic beat with a large amplitude is easier to get if a long solid body is tumbling. A weak and noisy beat is easier to get if a compact nucleus is buried in a lively coma. If a clean single period appears and stays stable over multiple nights, give a medium point to the design column. If the curve is messy with small peaks that wander, add a small point to the natural column. Finally, consistency across teams. A real effect survives new eyes. If multiple observatories reproduce the same width excess, the same quiet light curve, or the same orbit mismatch, raise the weight of those points. If an effect evaporates outside one pipeline, erase the point. Replication is the tiebreaker for everything on this card. What counts most? Two items sit above the rest: the thrust accounting and the fragmentation. Check. Together they carry more weight than color or limb sharpness. If gas can pay the bill and the body behaves like fragile rock at maximum heat, the natural story is strong. If gas cannot pay the bill and the body behaves like a smooth shell under stress, the design story earns another chapter. Here is a small ask. As the first plots land, try filling this scoreboard yourself and post your current tally in the comments. Keep it provisional and explain one choice you made. That simple habit builds a shared lab notebook for everyone watching. In the next part, we zoom back to the chemistry bench. We will explore why carbon dioxide and carbon monoxide can produce steep metal lines and sudden changes without intent, and where those explanations begin to strain. If you have ever watched ice on a spring pond, you know how physical systems pretend to have switches. For hours, the surface seems unchanged. Then the right minute arrives and a crack races across the sheet. Comet chemistry plays the same game. In a carbon dioxide heavy and carbon monoxide friendly coma, small thermal nudges can produce dramatic changes that look intentional even when they are not. Our goal here is to show how natural pathways can create steep metal lines, sudden color shifts, and on-off behavior. Then we will mark the places where that story starts to strain. Start with the surface. Interstellar radiation and micrometeoroid impacts can bake a thin crust on the outside of a nucleus. Think millimeters to centimeters. Under that crust sit ices and mineral grains with pockets of trapped gas. As the sun warms the skin, heat diffuses inward only slowly. For a while, the crust stays intact, and the deeper pockets stay cool. Then a pore connects to another pore. A micro crack opens. Warm gas reaches material that was shielded seconds before. Production jumps. Observers at Earth do not see the microplumbing. They see a steep rise in a line strength and call it a switch. The physics is just percolation with sunlight as the pump. Now add specific reactants. Carbon monoxide loves to bind to certain metal centers. Nickel is a classic partner because of its electron structure. On Earth, this chemistry is used to refine nickel at temperatures that would be surprisingly low for a metal vapor story. In a cometary environment, you do not build industrial molecules by design. You let sunlight and random contact do the work. If fresh surfaces with nickel-bearing phases face a local atmosphere rich in carbon monoxide, transient, volatile nickel compounds can form and leave the grain. Once in the gas, they are photolized by sunlight, and the nickel atom shows up as a clean emission line. Iron in a different mineral phase may not form equally volatile partners at that temperature. That gives you nickel ahead of iron without magic. It also gives you steep distance dependence because the formation rate increases very fast as the gas density and temperature cross a threshold. Porosity and grain size finish the picture. Fine grains heat and cool quickly, coarser grains lag. A surface made of mixed sizes and mixed minerals will respond in bursts as different populations pass their individual thresholds. That behavior can stack into a smooth power law when you average over many patches. It can also show up as sudden steps in small apertures that sample only a few vents. If a spectrograph slit is narrow and placed near the central condensation, you might capture a local outburst that looks like a switch. A wider aperture would see the same event as a gentle bend. The green color puzzle fits inside this box too. If carbon chains are depleted, C2 stays weak, even as overall activity rises. Cyanogen can grow fast with heliocentric distance because its parent molecules become available only when a thin thermal barrier erodes. That gives you a greenish look in some filters without strong C2. Dust scatter can bias broadband to the same hue. Narrowband images then reveal that the center stays white in continuum, while gas-dominated zones sit farther out. The result is a white midline with green shoulders when you stack frames in a way that emphasizes reflected light near the core. Where does the natural chemistry story begin to strain? First, persistence. If nickel stays dominant far past perihelion, while activity collapses and while carbon monoxide declines, you must invent new reservoirs or hidden heat to keep the pathway alive. That is hard to defend without independent evidence. Second, synchronization. If multiple independent metal lines jump in lockstep at a distance where no plausible thermal threshold sits, and where geometry has not changed, chemistry alone looks thin. Third, smoothness. A rubble pile with many vents should show hour-scale flicker in both continuum and some emission lines as rotation modulates which patches face the Sunday. A near-perfect monotone curve sustained for many days at peak activity would be unusual for an object with many random pores and fractures. There is one more experimental angle we should not ignore: laboratory analogues. Researchers can prepare powdered mixtures that mimic cometary crusts with silicates, organics, nickel-bearing phases, and frozen carbon dioxide along with trapped carbon monoxide. They can warm these analogues in vacuum and measure release rates and spectra. If such experiments reproduce early nickel without iron and a steep distance dependence under plausible temperatures, that would be a strong point for the natural model. If they fail systematically, the pressure would increase on explanations that need engineered surfaces. So the chemistry verdict for the scoreboard is conditional. Natural pathways can create sharp bends and even apparent steps when thresholds in heating, porosity, and reaction partners are crossed. Green without strong C, too, is possible when CN and dust are in play. Early nickel is plausible in a carbon monoxide-rich coma. The model begins to wobble if persistence, synchronization, or unnatural smoothness appear in multiple independent datasets. In the next part, we connect this micro-world to the macro path. Trajectories after perihelion will be posted soon by the orbit fitters. We will translate those tables into plain English, show how to compare the required thrust to what spectra say the coma can provide, and ask whether the path stayed hyperbolic or lost enough energy to hint at a lingering guest. When new orbit solutions appear, they can look like numbers spilled from a spreadsheet. Hidden inside are the answers to the biggest questions in this story. Did the object stay on a gravity-led path? Did outgassing nudge it in ordinary ways? Or did the path bend in a way that demands more momentum than gas can supply? You do not need a graduate course to read this. You need a calm eye and a few simple translations. Start with the elements that tell you the shape of the path. Eccentricity near 1 but still above 1 means a hyperbolic escape. That is interstellar by definition. If eccentricity moves closer to 1 but stays above, the object is still on its way out. If it crosses below 1, the path is now bound and the object will stay in the solar system unless later forces change that. Crossing below 1 would be a seismic event and would require a very large energy change. You also want to check the hyperbolic excess speed. That is the speed far from the Sun after gravity has done its work. If that number stays the same within uncertainties, nothing dramatic happened. If it drops meaningfully, energy was removed somehow. Gas can remove a little, not a lot. Next, read the residuals. Each observation contributes a tiny difference between where the model says the object should be and where it was measured. Orbit fit reports summarize those differences in arcseconds or in kilometers projected on the sky. Small residuals mean the model tracks the data well. If residuals are large and only shrink when a strong non-gravitational term is added, the fit is telling you that gas, or something acting like gas, is required. That is normal for active comets. What you compare is the size and direction of that extra term to the chemistry you see. This brings us to thrust accounting. Spectra give you production rates in molecules per second for gases like carbon dioxide, carbon monoxide, water, and for radicals like CN. Multiply the total molecular flow by the mass per molecule and by a representative outflow speed to get momentum per second. That is thrust. Integrate over time to get total impulse. Convert that impulse into a velocity change for a nucleus of plausible mass. Mass is the squishy part, but photometry and coma models put it within an order of magnitude. If the computed velocity change can pay the bill for the fitted non-gravitational term, natural jets pass the test. If the required impulse is 10 or 100 times larger than the budget, you must look for an error or for an additional force. Direction is as important as size. A sun-driven coma pushes mostly away from the sunday. The fitted extra acceleration should point roughly anti-solar on average, with gentle swings due to rotation and shifting vents. If the fit demands a push that points sideways for days or flips in ways that do not match any change in illumination, that is hard to square, with physics that starts and ends with sunlight. Extreme asymmetry in jets could in theory pull this off, but it would leave fingerprints in the light curve and in resolved coma structures. There is a subtle trap in all this: photocenter drift. If the nucleus fragments, or if a jet produces a long asymmetric dust fan, the measured center of light can shift a little away from the center of mass. That shift can mimic a trajectory change if not modeled. This is why the best orbit work is paired with images that check for multiple condensations and that measure the shape of the central coma. If there is a split, fitters often solve separate paths for the pieces. If there is a strong fan, observers can mask the fan and measure the core only. When you read a fit report, scan for a note that the team considered these effects. If they did, your confidence can rise. 1. Practical tip. When orbit updates post, write down 3 numbers in your own notebook: eccentricity with uncertainty, hyperbolic excess speed with uncertainty. A simple label for the non-gravitational term, such as small and sunward or large and odd. Then read the latest spectra and write down a 1-line thrust budget, such as gas can supply a few centimeters per second over a week. If your budget and the fit disagree wildly, do not panic. Wait for a second fit and a second spectrum. If the mismatch persists across independent groups, that is when you move a big chip to the side of the table marked something more. None of this implies hazard. The distances and angles do not intersect Earth. The purpose of this detective work is not alarm, it is understanding. The more you practice this translation, the more you will feel how gravity and gas write their signatures in numbers, and you can read, without anyone telling you what to think. In the next part, we turn to shape one last time, but with fresh tools. If deep space images deliver even modestly resolved pictures, limb gradients and measured widths will finally be more than a debate about processing. We will set thresholds for what counts as structure and what falls inside the blur of a point in a coma. Then we will look at how rotation can clinch the case with a beat that pixels cannot fake. The best thing about deeper space images is not the pretty pictures, it is the clean geometry. Even a modestly resolved view can end the argument about shape in a way that stacked rover frames never could. If a camera out past Earth's orbit catches the core as more than a single blurred point, we finally get to measure edges, widths, and how brightness falls off across the body. Numbers beat vibes. Here is how to read those numbers when they arrive. Start with the point spread function. Every optical system smears a point of light into a small blur. Calibrate that blur using nearby stars in the same exposure. Measure the full width at half maximum of those stars. That is your yardstick. Now measure the width of the central condensation across the suspected long axis and across the short axis. If both widths match the stars within uncertainties, the nucleus remains unresolved. Any elongation you see in longer stacks is likely motion, smear, or processing. If one axis is consistently wider by a clean and repeatable factor, you have an extended source. The question becomes, how extended? Next, look at limb gradients. Draw a line across the bright core and plot intensity versus distance. A compact solid wrapped in a thin coma produces a steep shoulder near the limb, followed by a softer skirt from gas and dust. A pure coma with a tiny unresolved core produces a gentle slope with no crisp break. Compare the observed slope to a simple model that adds a point source to a 1/r to some power coma, and then convolves with the measured blur. If the observed shoulder is steeper than any point plus coma model can reproduce, structure wins a point. Orientation matters as well. If the extended width keeps a fixed position angle over a series of short exposures, while the tail and sunward features swing with geometry, that suggests a body axis rather than a transient plume. If the apparent orientation drifts with the anti-solar direction, it is probably gas. This is where time series beat single frames. Ask teams to post sequences, not just the sharpest still. Color can help. Repeat the width and limb tests in a dust-dominated continuum filter and in a gas-dominated narrowband filter. A solid core should look broader relative to stars in the continuum. Gas should add width in the narrowband. If the width excess lives only in gas images and vanishes in the Rapai continuum, the apparent elongation is likely a jet or a narrow sheet of dust. If the width excess persists in the continuum with similar orientation, take notice. Now, bring in rotation. Shape writes its own music. A long body that tumbles presents a large changing area to the sun and to us. That modulation creates a repeating beat in short exposure photometry. You can measure it from the same deep space platform or from ground telescopes once the object is back in view. A strong single period that stays stable night to night is a signature you cannot pull out of static smear. If the amplitude is large, the implied aspect ratio is large. If two periods appear in a neat ratio, you may be seeing principal axis rotation mixed with precession. That complexity can still favor structure over a featureless point. There is a cross-check between edges and beats. The rotation period that the light curve reveals should be consistent with any changes in the resolved orientation of the elongated core across a sequence. If the limb angle drifts in step with half the photometric period, that is what a baton does as it tumbles. If the limb angle follows the sun instead, it is gas painting the blur. Be greedy with calibration details. Every claimed edge measurement should come with plate scale, star widths, exposure times, filters, and the exact code used for profile extraction. Ask for the radial profiles as a plot, not just a sentence. Ask for the models that mix a point with a coma so you can see whether the observed shoulders really are too crisp. Replication is the last gate. Two teams with different instruments should be able to reproduce the same width excess and the same profile shape when they match filter and exposure strategy. One more reminder about safety while we chase edges. Nothing in these measurements changes the geometry with Earth. You can be thrilled by the detective work without being anxious about risk. In the next part, we take the whole case and compress, pull it into a viewer-friendly map. Not a verdict. A navigation chart you can use to explain this story to anyone who joins late. What happened, what we know, what remains open, which tests will matter next. Then in our final part, we close with why this debate is good for science no matter which column wins. Let us make this simple and shareable. Imagine you have 90 seconds in a conversation to explain why a streak in a rover stack turned into a global debate. You need a clean map. Here it is. What happened, what we know, what remains open, what to watch next, and where you can plug in without waiting on anyone. What happened is the easy part. On an early October date, a rover on Mars captured a sequence where a faint visitor streaked across the sky. People stacked the frames and saw an elongated white stripe with green hints near the edges. The internet split. Camp 1 said camera smear. Long stack, fast object, classic streak. Camp 2 said hold on. The center is stubbornly white while green lives at the edges. The width and the edges look too crisp, and metals in the spectra sound wrong. Silence from several space agencies during the best viewing window poured fuel on the questions. Then the object slipped near the sun from Earth's point of view. That is where we stand. What we know rests on data that survived the hype. Spectra indicate a coma where carbon dioxide and carbon monoxide are strong while water is relatively weak. CN appears to carry much of the green impression even when the classic green maker C2 stays low. Nickel lines turned on earlier than iron and rose steeply with decreasing distance. Those facts alone do not require anything artificial. Chemistry with thresholds can mimic switches and can separate nickel from iron if the minerals and gases line up. Amateur observers confirmed a green halo and a white continuum bright core in many sets, and they showed that short stacks keep the width near star widths in most cases. None of that proves shape. All of it constrains the story. What remains open sits in 4 boxes. Shape. We still lack a clean resolved core that would show edges without heavy processing. Dynamics. We still await post-perihelion orbit fits that will reveal whether a modest sunward push can explain the track or whether something extra is required. Metals and ratios. We still need to see whether nickel eases and iron catches up as heat retreats, or whether the imbalance persists past what normal chemistry can sustain. Light curves. We still need a clear rotational beat with enough amplitude to imply a long, rigid body, or the lack of such a beat that fits a compact core in a lively coma. What to watch next is your checklist. First, orbit updates with uncertainties and a non-gravitational term. Read the eccentricity, the hyperbolic excess speed, and the direction of the extra push. Compare to a thrust budget from measured gas production. If gas can pay the bill, natural gains ground. If not, the debate escalates. Second, spectra before and after perihelion from independent teams, with continuum removal and error bars. Follow the nickel and iron curves. Look for symmetry with distance. Third, resolved images from deep space platforms with star-calibrated widths and limb profiles. If the core stays point, like across filters and exposure sets, smear explains the stripe. If it is extended in continuum with crisp shoulders, geometry changes. Fourth, light curves with hour cadence stitched across nights. A strong, stable period favors structure. A jittery profile favors a small nucleus inside a busy shell. Where you can plug in is right now. You can run the scorecard we built 2 parts ago as new drops appear. You can ask creators and missions for calibration details rather than viral crops. You can invite friends to learn what a point spread function is in 1 sentence. It is how wide a star looks through a given camera. You can help your feed by amplifying posts that show raw frames and methods, and by ignoring captions that shout proof without numbers. If you are part of an observing club, pick a narrowband filter and a continuum filter and plan a replication of the width test as soon as the object returns to darker skies. If you are new to this, pick one plot, such as the nickel ratio, and track it like a sports fan tracks a favorite stat. 2 gentle reminders. Curiosity does not require fear. The geometry with Earth remains comfortable. And uncertainty is not failure. It is the honest state of a field when data are midstream. This is how science looks between a surprise and a paper. Here is a small challenge to close this map. In the comments, write 1-sentence prediction for each of the 4 open boxes. Shape will be unresolved or extended. Dynamics will demand small or large extra push. Metals will normalize or persist. Light curve will be noisy or smooth. Tag your post with my map so we can find them and pin a few. When the next wave of data lands, you can grade your own call and become part of the shared lab notebook. In our final part, we will zoom out. No matter which column wins, this story is already a win for how we ask questions in public, how we weigh evidence, and how a planet full of curious people can do real science together. If you have stayed with us through the streaks, the spectra, the statistics, and the silence, you have already felt why this story matters. It is not only about what this visitor is, it is about how we find out. The process has been messy in public. That is good. Science has always been a contact sport played with ideas. What changed is that millions of you now sit courtside, and sometimes you pick up a ball and take a shot. A viral clip pulled millions into questions that usually live in seminars or in late-night Slack threads among instrument teams. Could a stack create a shape? Can chemistry separate nickel from iron? How steep is too steep for a production law? You watch people argue, run numbers, and update their priors live. You saw careful posters get buried by noise some days and lifted by replication on others. You saw how a single raw frame can be worth more than 100 hot takes. You saw what it means to say we do not know yet and still keep moving. You also met the limits of patience. Agencies and teams spoke cautiously, even when your feed was on fire. That restraint felt like evasion at times. It was discipline. Calibrated data beats thrilling rumors every day of the century. When your grandchildren open a textbook, they will not read the threads. They will read a paragraph written by a team that waited to get it right. The tension between a hungry public and a careful pipeline is not a flaw to be fixed. It is a balance to be tuned. The more we all reward methods over vibes, the easier that balance becomes. Most of all, this debate has been a masterclass in how to hold two ideas in your head at once. A natural comet with odd chemistry can explain much of what we see. An engineered object is a live hypothesis only if natural explanations fail under weight of evidence. You learn to separate what is consistent with from what proves. You learn to let a beautiful possibility wait its turn. That is not cynicism. That is respect for reality. There is a bigger payoff too. We built a shared toolkit that will outlast this visitor. You can now read a spectrum like a pro. You can scan an orbit update and translate it into plain language. You can look at a processed image and ask for the star widths and the plate scale. You can check whether a claimed thrust can be paid for with gas. That is power. It means the next time a cosmic mystery lights up your screen, you will not be at the mercy of sensational captions. You will do your own first pass and help others do theirs. So where does that leave us? With curiosity and with a plan. In the weeks ahead, we will grade the scorecard together. If the post-perihelion path fits a modest sunward push and the metals relax as heat retreats, the natural story strengthens, and that is wonderful. We will have met a messenger from another star and learned chemistry our own backyard seldom shows. If the path bends beyond what gas can supply, or if shape refuses to collapse into a point even in clean continuum, then the conversation changes, and we will follow the evidence without flinching. Either way, the win is knowledge that has been earned in daylight with millions of witnesses. You helped make that daylight. Every request for raw frames, every polite challenge to a claim without methods, every careful replication made this investigation better. If you want more work like this, tap subscribe and share this deep dive with a friend who loves hard questions. If you have a prediction, post it now and come back to score it when the next data drop lands. Your comment will not be lost in the noise. We read these and we learn from them. There is a final reason to keep watching. Interstellar visitors are not rare forever. Our instruments are getting faster. Our sky surveys are becoming deeper and wider. This century will likely bring dozens of such objects into view. Statistically, some will be routine, and a few will be beautifully strange. When the next one arrives, you will already know how to think, how to test, and how to keep your wonder intact while your standards stay high. Until then, keep your skeptical kit handy, and your sense of awe switched on. The sky is not done with us, and we are not done with it.